investing some amount, and I want to take it on 2nd.
2nd of February.
Yeah. Because I expect that because of Corona and the forthcoming election, definitely there will be some scopes for investment.
Actually, yesterday I was because I was listening to so many videos and all in the stock market.
Yes.
There is one person, actually, I do not know whether you have seen, Sharik Samsudin. He's beautiful talk, actually. He has given a series of videos, actually, how to...
Dr. Prasad and Bala, I made it YouTube also live. So,
hi.
Yeah. So, just we can wait for some time so that we can.
No problem.
Okay. So, I had shared that this thing. I'll share it with you, actually. It is a very good... he has given a very good video series, actually, talking about the technical analysis and all. How to do a good technical analysis.
Actually, in our yesterday Times of India, because Sensex touched 50K, I think 4 to 5 full pages were on the investment. Those who invested in gold, maybe 15 years back. Those who invested in real estate, what state it's going, and maximum gainers are in the last 9 months. So when the Sensex went to 27 or something, and it is almost touching 50 minutes. Big
actually, yesterday you see, yesterday market was down.
Yes.
And it started day for yesterday. The last 1 week actually was down. Monday it was down. Tuesday it went up. Again it went down.
No, it is already live. YouTube is already live. So internal matters can be discussed later.
Okay.
Are we live now in YouTube?
Yeah. Good morning. Good morning. Yeah. Okay. Okay, fine. Okay. Okay, fine. Yeah. So I think we have another 8 more minutes. 8 more minutes to start.
Yes.
10:52 now.
Yeah. Just a second. I think live streaming is started.
Yeah, it started. Yeah.
Yes.
Yeah, we have another 2 more minutes. Yeah, 10:58.
Yes, Professor. No problem.
Dr. Prasad, once your introduction is over about Bala Subrahamanyam, then you can exit from that. You can directly look into YouTube.
Okay, fine, fine.
Okay, so that Bala Subrahamanyam video will come.
Okay, fine, fine. Yeah, we can start. So, good morning to all the esteemed members of the Ocean Society of India, ladies and gentlemen. The Ocean Society of India has taken up a noble initiative for conducting the OSI webinar series. Under this event, there would be one talk arranged every month from eminent scientists, engineers, academic professionals working in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, preferably on a weekend, that is Saturday. That would be convenient for many of us to attend. This webinar series is targeted mainly for the students, researchers, scientists, engineers, and working professionals in the field of atmospheric, oceanic sciences, and ocean engineering disciplines, with a motive to impart and improve the knowledge benefiting the OSI community. I thereby earnestly request all the participants to actively get involved in all the lectures under the OSI webinar series that would be held every month. On behalf of the Ocean Society of India, it is my proud privilege to welcome my good friend, Dr. D. Bala Subrahamanyam, scientist, Space Physics Laboratory, Vikram Sarabhai Space Centre, Thiruvananthapuram, today for the invited talk as a part of the OSI webinar series. We had a total of 3 talks conducted last year as a part of this initiative, and this being the first talk of this year. On the personal front, myself and Dr. Bala Subrahamanyam had a good association since 5th of May 2003, when we joined together as project scientists at INCOIS, Hyderabad. Good old memorable days. I was particularly impressed with his motto in life, never ever give up. He is a researcher by profession and philosopher by nature. Following 2 simple rules in life: try to change the things which you cannot accept, and try to accept the things that you cannot change. Dr. Subrahamanyam is a very serious researcher having a strong background in atmospheric boundary layer and associated dynamics. He is a dedicated scientist having a strong flair with a proven track record and very impressive list of peer-reviewed journal publications in very high impact factor journals that demonstrates unequivocally that he has special skills and abilities in the field of research. Dr. Bala Subrahamanyam completed his Master of Science in Physics with specialization in electronics from Pandit Ravi Shankar Shukla University, Raipur, India in 1996, and Doctorate of Philosophy in Physics under the Faculty of Science from Mahatma Gandhi University, Kottayam, India in 2004. He joined as ISRO Research Fellow at Space Physics Laboratory, Vikram Sarabhai Space Centre Department of Space, ISRO, Thiruvananthapuram during 1998, 2003, and later continued as a research associate at SPL for 2 months. That is during the period April 2003 to May 2003. Dr. Bala Subrahamanyam joined as a project scientist C at INCOIS, Hyderabad during the period 2003 to 2005. Thereafter, he worked as an invited scientist at Ocean Climate and Environment Research Division of Korea Ocean Research and Development Institute, Seoul, in Korea from February 2005 to February 2006. Dr. Bala Subrahamanyam joined SPL VSSC as scientist SD in March 2006 and presently scientist SF in the same organization. His research interests include wide topics such as boundary layer meteorology, the regional atmospheric modeling, tropical cyclones, parameterization, large Eddy simulations, nowcasting, and short-range weather predictions, air-sea interaction process. Dr. Bala Subrahamanyam was very actively involved in major projects and programs of ISRO, such as the weather prediction in support of PSLV and GSLV missions. Since 2008, he is a member of the Inter-Center Weather Forecast Expert Team, investigator in numerical simulations through COSMO in support of ICARB 2018 experiment, commissioning of open path carbon dioxide measurement at Kodaikanal and Ponmudi, and many other administrative positions at SPL VSSC. Dr. Bala Subrahamanyam was quite active in research supervision of many PhD scholars and postgraduate academic projects. He is a member in various important committees, such as the Review Committee of Science Data Processing Pipelines for the Chandrayaan-2 payload, Functional Committee for the World Space Week and Digital India Week celebrations, and SPL Academic Committee, and many others. Dr. Bala Subrahamanyam is a core member in the Inter-Center Weather Forecasting Expert Team, constituted by the Satish Dhawan Space Centre, Sriharikota, for providing the short-range weather prediction in support of ISRO's PSLV and GSLV missions. The team was constituted for the very first time during the PSLV C-11 Chandrayaan-1 mission in October 2008, and since then he is continuing as one of the core members and have supported a total of about 40 missions. He is a lead guest editor in journals like Advances in Meteorology for the special issue on atmospheric boundary layer process and atmospheric modeling, and reviewer of many peer-reviewed journals. He was also a guest faculty at the Indian Institute of Space Science and Technology, Thiruvananthapuram. He has published more than 50 research papers in peer-reviewed high-impact journals and life members of many professional societies. With this brief introduction, it is my proud privilege to kindly invite our speaker for today, Dr. D. Bala Subrahamanyam, to deliver the talk. Also, kindly note the question and answer session will be attended after completing the talk, and the questions can be messaged in the chat box. Thank you.
Thank you very much, Sir Prasad. It's my proud privilege and honor to present today here, and thanks a lot for so elaborated introduction. I may cut short into very small that I am a researcher who is trying to learn something each and every hour, each and every day. So with very brief introduction, I will try to share my presentation. Can you please confirm whether my presentation is seen? Prasad, whether my presentation is seen?
Yeah. Yes.
Okay, thank you very much. So let me start my presentation. My presentation's title today, what I have chosen, is the role of atmospheric boundary layer in air-sea interaction processes. If I go slightly to detail about the topic, it contains two keywords: the atmospheric boundary layer and the air-sea interaction. To be honest, these two topics are extremely loaded topics. Atmospheric boundary layer itself is a topic of investigation for years. So is the air-sea interaction. And my job is to probably introduce to the audience to these two complicated subjects in probably a plain manner, so that they can appreciate why do we need to study the boundary layer and why do we need to understand the air-sea interactions. So what I do here is, if I go to the word boundary, it looks very, very simple, and it looks like that there is nothing to understand in this particular area. For here, what I am showing here is, this is the Madhya Pradesh district maps. What you can see is different colors are put up, so we can clearly say that this is my district, this is another district, kind of things. So boundary becomes very clear. If I come to the cricket field ground, this is the boundary, which is very clear that if somebody is hitting a balls out of this boundary, that is called the 4 or 6. And if the ball is stopped in between, it is not 4 runs. In another perspective, if I look into the road map here, this is supposed to be the left lane, this is supposed to be the right lane. We go here, and the other people will be coming from here. So things look extremely simple as far as the term boundary is concerned. Now, if I expand it to boundary layer, the complexity starts. Look here, in the left side, what I am showing here is a cricket fielder is trying to stop the ball. We do not know whether he has touched the leg or not, but that becomes the question of concern, that whether we should give 4 runs, or we should give the catch out, or we should give the 6 runs. Same problem comes in our roads when the people, either legally or illegally, go from one side to the other side. It leads to a probably chaotic situation where the actually prescribed rules are violated. So the term boundary layer, it comes with 3 asterisks. That's why I'm putting the terms and conditions apply, where the spatial scale as well as the temporal scale comes into the picture. So the boundary layer, even though we think it is simple, but it is not so. Now I am going to put a very simple picture here. All of you will be able to guess what is this. This is our Lok Sabha numbers. Different colors are put up here to represent the different parties do exist. But the question which I want to put here is, can we distinguish one party from other? Answer is very easy. Yes, I see the orange color, probably it is one party. Blue color, it is another party. So it is easy to distinguish that one member of a party and another member, probably this may be from Congress, this may be from BJP, and all the parties, if I take any 2 parties, they have distinct qualities. And one member is not supposed to jump to another side without following some standard procedure, which we call the Indian Penal Code. And there are different rules, kind of things, but fortunately, this is about the politics. Where the rules, I have put the yellow color, rules are very, very robust. You can see here, when I say the robust, the important and funny part in the next slide is, all the rules are subject to change without any prior notice. Fortunately, but unfortunately, that was politics. Now we are dealing not the politics, we are dealing the physics. So how do we define these particular boundaries? Now, if I say that how the boundary layer forms, or what is the so-called boundary layer, first thing which comes to my mind is the clearly visible boundaries. Here I am going to show you 3 pictures. First one is a rock where different kind of layers you can see from the colors. Second picture is a very beautiful and melodious cake, but you can see that you can eat the part by part. And one more is on 15th of August, our Air India will be doing extremely brilliant air show where they put different kind of colors. If somebody asks that where do you see the clear visible boundaries? Yes, I see here, probably gray color, the red color. Same is the picture here. If I am eating this cake, I can say that the bottom layer, the middle layer, the top layer, and probably the topping, they are different. Here colors can give a discrimination that one part is different from other. So if I put this particular concept in the physical terms, whenever a fluid is one which can flow, interacts with a solid or another fluid, it leads to the formation of a boundary layer. As simple as I said, what we need is a fluid, and it has to interact with a solid or probably another fluid. Now, if I am talking of 2 fluids, definitely they should not be the same fluid. So this boundary layer can form if a solid and solid comes, that is like this. You can see the distinct boundary. Here fluid is not there. Solid and liquid, solid and gas, liquid and liquid, liquid and gas, gas and gas. So in definition point of view, a boundary layer is defined as the layer of fluid in the immediate vicinity of a material surface where significant exchange of momentum, heat or mass can take place. This is what the question boundary layer comes. Now, if I want to say what the atmospheric is, so I need to word the one more word, atmospheric. I already explained in the previous slide, boundary layer we need one materialistic surface, and we need a fluid. Here what we have is the earth, which is a mixture of land as well as the ocean. So that behaves like a material surface, and the just atmosphere above that behaves like a fluid. So when these two things interact, we get the formation of the boundary layer. So if someone asks to define what is the atmospheric boundary layer, it is formed as a consequence of the interactions between the atmosphere, that is the fluid, and the underlying surface, that is land or water. The concept looks very, very simple. But the problem comes is this atmospheric boundary layer takes more than 50 percentage to 80 percentage of the incoming radiation. It eats away. Whatever processes we carry forward in the radiation, it will take away huge amount of your energy. So we need to understand why is it taking this much energy and what will be its consequences. So if you go for any examination and someone says that please define the atmospheric boundary layer, I would suggest two famous books. One is by J.R. Garrett, another by Roland B. Stull, where the clear-cut definition of the boundary layer, that is the atmospheric boundary layer, is given. I am just going to read for the younger generation. The atmospheric boundary layer is the layer of air directly above the Earth's surface in which effects of the surface, which is underlined here, they are felt on the time scales of about a day. So gradually the complexities comes is not only interaction, we have to look for what is the time scale. If time scale is about 1 day or probably less than that, it will also allow significant exchange of momentum, heat or matter. But one question, whenever I get this particular definition, I ask myself, how nicely these definitions have come. But how did these authors can write such a beautiful definition? The answer comes, above definitions are arrived after so many years of research and development. So what you are getting, the final product, is lot of efforts have undergone behind these definitions. So today we will try to understand what are those efforts and why do we need to study this atmospheric boundary layer. Now, as I explained in the previous slide, the atmospheric boundary layer, the small what you were seeing just above the things, this plays an important role in the air-sea interaction. What is the meaning of air-sea interaction processes? Here I am going to put a cartoon here. What I am going to show here is, if you take the sun here, which will be with us about for 12 hours from sunrise to sunset and then goes back, it gives the radiation, that is the incoming solar radiation. A part of that goes back as the terrestrial emission, and then part of that goes to the sensible heat flux, and then part of that goes to the latent heat flux, and then something will be absorbed in the soil heat flux. As long as this arrows, I am not putting a number. Things are very simple. I can put them in the equations. But the complexities comes if I want to put the numbers. Then somebody will say, what was the incoming radiation? What is 800 watts or 900 watts? Depending on that, your L will be there, H will be defined, LV will be defined, and further G also will be defined. So ultimately, these methods which we are showing, of course, it looks to be simple, but once you put the quantities, it becomes very, very complicated. For example, here you can see two different kind of soils. One is the dry soil and another is the wet soil. Dry soil, if you are going to the desert region, you can see that it will be very, very hot. If you are going the barefoot, your legs will get the heat. But important point is, if you want to explain in mathematics or physics, how do you explain that this is very, very hot soil and the other one which I am showing is the kind of wet soil? Because if you have a dry soil, your sensible heat flux will be large, and if you have wet soil, your sensible heat flux will be very low. So what is the meaning? What should be the magnitude of sensible heat flux? Depends on the underlying factors. And more crucial and complex if you go to the area of modeling. How do you explain to a model which doesn't have the eyes, which doesn't have the ears, which doesn't have a tongue, to explain that this is dry soil, this is wet soil? For that, in the area of modeling, the right side table, we go for the bulk aerodynamic method. This bulk aerodynamic method will grab some numbers and eventually it will calculate the fluxes. But more problem comes is if you are over an ocean. Over ocean, everything below you is just water. You do not have any differences that dry or wet kind of things. But the difference comes in the wind speed, the sea characteristics, salinity, and there are many other factors which discriminate one part of ocean from another part of ocean. If you are going for the shallow water, if you are going to the deep ocean, these exchange coefficients definitely change. And ultimately, if I go to the exchange coefficients, they are bread and butter of the atmospheric boundary layer. That's why I choose the topic atmospheric boundary layer and its interaction in the air's interaction. So now I am trying to give a flavor of what this atmospheric boundary layer, today's definition, how did we come to that one. For that I will tell a very small story, very famous story. It was a story of almost 308 to 215 BC before Christ, when one King Hero was there. He ruled like the very nicely, and he won lot of battles. And eventually he decided that I have done very good work, so I should thank God. How can I thank? He said, I will make a very nice crown. So he took out the gold, he weighed it, and he called one goldsmith and he said that please make a crown for me from this one. But the story starts now. What is the great here? Some king is there. He takes the piece of gold, which he definitely will be having, and he gives to the goldsmith. The story starts here. The king suspected when the goldsmith gave the crown was very beautiful, but somehow king's sixth sense told that, looks to me the amount of gold which I gave to the goldsmith, this fellow did not use it. He probably mixed up something and he has given a very beautiful crown, but not used all the gold what I gave it to him. So the bottom line is the corruption which we are trying today, even in 275 it was there. The problem now is king has a suspicion that there is something problem is there, gold has not been used. So he called all his ministers and he has thrown a difficult challenge. He said that first of all, this crown is very difficult, very beautiful, don't destruct it. But find it out whether this crown has used all the gold which I gave or not. So that was a very difficult challenge, and ultimately, one mathematician, Archimedes, he accepted. The challenge was you should use the crown, but you should not destruct the crown. And you should find out that how this particular crown, whether it has used the proper gold or not. So what happened is the toughest part was you should not destruct. Then Archimedes puts his brain and he decided that the weight of silver and the weight of gold both will have different densities. So probably if you dip something into the water, equal amount of water should come out. And if there is a mixture, it will definitely lead to some kind of impurities and different kind of water will be coming out. But this idea came out when he was just going to bathtub, he dipped himself and suddenly water came out. And the moment water came out, he said, come on, eureka, eureka, eureka. I have got the lesson, I have got the answer. How he got the answer? He said that what is my weight? Accordingly, that much of water is displaced. So if I can find out how much of water displacement will be there for the gold, I have got the answer. But the important thing, this great idea came just like that, and more important, that was beginning of something called the fluid dynamics. I call it 250 BC. The first idea of the fluid dynamics, the credit goes to Archimedes, who said that water displacement should be quantified. What next? If you go further, probably in the 15th century, there was a very beautiful painter. You all may be knowing that Leonardo da Vinci. There are a lot of controversies here. I am showing you here two important pictures. One, what he did is he was sitting in the kind of field and he used to draw a lot of paintings, and he saw one gutter water. From gutter water is continuously flowing, and he saw there is some pattern here. But you can show here some swirls are coming. He did not know what is the swirls. He drawn it. And these paintings became one of the challenging tasks for the physicists who are coming in the next generation. Important point here is the 15th century, the observation of the fluid was made, but it was not understood. That was in the 15th century. Now, if I go to the 16th and 17th century, which I call the actual complete shaking of the physics, that started from the great scientist called Newton, Sir Isaac Newton. His name is always pronounced with the prefix Sir. So Isaac Newton, who gave the first recorded literature that was called the Principia Mathematica, that was the first available literature where the mathematics was mixed with physics, and he defined that all the rules of physics should be put in the mathematical sense. And this gave rise to important things, that whatever we know about the physical processes, someone should put the mathematics to that, and that should be solvable. And mathematics, the problem and the solution is one problem can have an easy, good solution. So the Principia Mathematica gave rise to the opening of a new era where our understandable things we can put into the mathematics. That was in the 17th century. Now, if you remember your MSc class or probably BSc class, we are taught about one pipe experiment. If you are putting the flower water kind of things, if you press that, the flow increases. The important concept was as the diameter of the pipe decreases, the flow will increase. Looks to me very simple, but Bernoulli put forward in the equations. And these equations were actually referred from the Newton's equations, which were put up earlier. So that means Newton opened up a new era. And this new era was leading to different kind of fluid dynamics. Bernoulli deserves very great credit for putting forward this concept of fluid dynamics, which actually gave rise to a new concept later, which I am going to cover up next. Now, if I further go to the 18th century, two important scientists, one was the D'Alembert and Euler. I definitely give the credit to them for their comprehensive work, which gave complete equations, the complicated equations, and it also led to one thing that if someone wants to do physics, he has to understand the mathematics. And that was the famous Euler cup. If you see Bernoulli, Alembert, and Euler, they started putting that the fluid dynamics concept, we should deal with the pressure and velocity fields. The equations what I am showing here in the cup, they are just the gist of this one. But important point, the 18th century, people started appreciating that fluid dynamics, we have to have master in the mathematics. If we are not the master in the mathematics, we will not be able to define this one. The 19th century, the problem came with the most important equation of fluid dynamics that was called the Navier-Stokes equation. This Navier-Stokes equation, basically, it was taken from Euler, but the Euler, one problem what Euler could not solve was he did not account for the effect of friction acting on the motion, and he ignored the viscosity. Viscosity is the one term which defines how much thick the fluid will be. So Navier and Stokes together, they put up the equation which we call the Navier-Stokes equation. They were first derived by Navier in 1822 and later by Stokes independently in 1845. We put always the together. These equations were the birth of the actual fluid dynamics. But the problem in this Navier-Stokes equation till date, how do we solve with this? What are the terms? We are to understand this one. And this gave rise to that how do we explain and how do we try to understand the fluid dynamics. But this Navier-Stokes equation, even though it was put forward in the 19th century, the problem was inability to solve this. All the people took these equations. Even today, if somebody is trying to go to the atmospheric science or in the oceanic science, if you are going for one interview, take it from me, definitely one question will be, can you write down the Navier-Stokes equation? So the problem here was, how do we solve this Navier-Stokes equation for the practical problems? I have a book with the Navier-Stokes equation, maybe about 300 pages. At the end, it says that some problems and some terms are ignored here, which will be dealt in the next paper kind of things. So eventually what happened in the 20th century began with a kind of frustration that we are not able to solve the Navier-Stokes equation, which is required to understand what is a fluid dynamics things are doing kind of things. And the 21st century, or I can say 20th century started with kind of race between the theory and the experiments. Here I am showing that Orville Wright and the Wilbur Wright, the famous Wright brothers, very famous for flying the first aircraft. They were literally fed up that somehow we have to fly one aircraft which should go to some height. But the problem for them is the design of that aircraft. They were struggling, they were putting the wings here, they were changing the triangular direction, they were making the rectangular, they were trying to semicircle, but they were failing basically because they were unable to find out how the air will be interacting with these fluid wings. And the answer comes here, no invention waits for a theoretical explanation for long. As and when the right time comes, the invention takes place in due course. Now, if someone asks, probably my mentor here, Dr. Ravichandran is here, he will definitely appreciate one thing. If someone asks me, where do you have seen the maximum inventions? I will say ORV Sagar Kanya, our anchor ship. And if you go to the engineering unit, all the people who are sailing in the Sagar Kanya, they do not have any market there. They will go with the problem that I want to make one screw here, which should be looking like that. They will give without any design, and the engineers and the technicians, they will come out with a solution. The reason is no other opportunity. You have to do whatever you are there. So invention doesn't wait for any theoretical explanation, and that is what happened here. Wright brothers did not know how to solve Navier-Stokes equation, but on 17th of December, they succeeded in flying the first aircraft, and that was written in the milestones of the fluid dynamics and the aerodynamics that Wright brothers succeeded in flying the aircraft, even though it is the truth that their aircraft had lot of problems. That was the beginning of the 20th century. Important, note down the date, 17th December 1903. Now, when I said 1903, let us also look at what was happening around. Now I go a little bit beyond. That was August 8, 1904. The venue was Third International Mathematical Congress at Heidelberg, Germany. Just 1 year later, one humble scientist who happened to be of 29 years, he presented a paper titled in Germany, which translates as On the Motion of Fluids with Very Little Friction. And what I'm going to show here is a very, very domestic kind of experiment. What you see here, it is a water tank, completely, very lengthy. In between, he put an iron tab so that the water from the top and bottom can be discriminated. He put a cycle wheel here. Further, he put some copper straws here, and he used to rotate this particular wheel very fastly. So water will go from here, come from here, go back here, and whatever the copper threads you are putting, based on that, you can understand how one particular fluid is going. To make the complicated things, he put little bit of wheel which was attached here, and due to that, how the fluid is moving, he happened to see that. But thing was, he was a junior scientist and he was told that your presentation is for only 10 minutes. So he just made extremely less number of slides, the transparencies, and in 10 minutes presentation, he put forward this experiment and he explained that this is the solid surface, and this is where he was getting the liquid, which happens to be the water and the kind of fluid. And this particular arrows he could picturize from the copper sheets. And he told that if I look into the velocity, at the surface, velocity looks to me zero, but as the velocity is going above, the velocity is increasing and it becomes to the maximum possible at one particular height. And this particular point is the point of touch, and this is slightly above. He did not know what is happening here, but he said there is a layer which definitely is not exactly like solid and not exactly like liquid, something different, something very, very different. This picture I have taken from his own original presentation. So he explained that whenever a liquid is interacting with a solid, there is something happening, and that he said that it is a layer. Now, if I look into the modern world of aerodynamics and the fluid dynamics, till date it is very much dominated by this Prandtl's idea. And all rights, he deserved a Nobel Prize in the area of boundary layer. But the unfortunate part was Dr. Prandtl never got any prize. He was never recognized for what actually he deserved. And some people even say that Nobel Committee was reluctant to award a Nobel Prize because it was in the accomplishments of the classical physics. So very satisfactory explanation what Ludwig Prandtl provided, he could not gain actually what was supposed to be given to him. And ultimately, this presentation was in 1904, and eventually he sent the proceedings, which many of us do. They sent the proceedings and he got published. And almost after some 24 years later, this 8 pages long paper, it was picked up by the famous fluid dynamicist Sidney Goldstein. And he asked Prandtl, why did you write so small? He said that, sir, I was given only 10 minutes, so I believed that I should not write too much. I should write only what I am supposed to write. And that is what Ludwig Prandtl was about. He died in 1952, but his life was always very simple life. And if someone asks me, what do I appreciate this paper about, or why do I appreciate this paper about? First number, this was presented a new concept in 10 minutes. Second number, he used the word transition layer, not the word boundary layer. Third things, boundary layer term later came into the frequent usage by Prandtl student, not the Prandtl. Prandtl never claimed that I discovered something. And this seminal paper was prepared in his mother tongue. So now look at that 1928. this much time people took to understand, let us also look at what was happening around at that particular time. So I will gradually take you to the away and I will take you to a different topic, but you will appreciate later that why I am mixing it. Here you remember the year 1928. I slightly forward the year 1914, that is about 10 to 15 years back of 1928. There was a famous king, Archduke France, who happened to be from 1863 to 1914. He was the Austro-Hungarian Empire. He was born in Austria. On 28th of June, this gentleman was killed by some people who were not liking him. Along with his family, this happened to be his court. He was going in one kind of buggy. They finally caught him and they killed. The history says that this assassination was attempted even earlier. And remember the date here, 28th of June 1914. Science was advancing at its own pace. The political rivalry also was increasing. So 28th of June, one king gets killed at morning 10:45 a.m. What proceeded next? Within 1 month, the so-called World War I began. And those who know the history, they will always find the linkage of France. Because of France assassination, the rivalry began and eventually it became 4 years big effort of World War I, 1914 to 1918. Why do I want to tell this here is science was there 1904 presented, but it never got importance. One king got killed and immediately people reacted within 1 month, which led to a very big world war. That was 1918. If I further go for fast forward, eventually the rivalry was further going above and Second World War took place between 1939 to 1945. And this was the very big world war where the Hiroshima was bombarded with the atomic bombs. People still in Japan struggle for the skin disease. But important point, 1945, such so much big rivalry took place. Somebody should question what was happening to the science. That is the point which I want to communicate here. Those who have been to the ages of 1980s and 1990s, which I definitely belong to, and some of the my colleagues will also see, they will definitely remember we used to have the USSR era. USSR era was dominated by Russian books. We always used to have the Russian exhibition of books where the books will be very cheap. 10 rupees, 5 rupees, you will be getting very good quantum mechanics. And there was a gentleman called Mikhail Gorbachev. His famous picture, his head was almost one map kind of things. And this dominated by USSR. One important thing was these people will do whatever in the Russian language. They will not adopt the English language. Still, despite that, the translated books were available for very, very cheap price kind of things. So what was happening in this particular time is race between the USSR and the America. They were saying that who will go to the moon first, who will go to the space first. So important thing was one part Russia was there, which was trying to lead. Another part America was there, which was trying to lead. They were trying to compete with each other. USSR was dominating with the mother tongue. America was dominating with the English language. But eventually what happened in this particular period, I call one post-war scenario, that was 1946 paper. That was by A.M. Obuko. I cannot pronounce what exactly he wrote here, but if I translate into English, it meant turbulence in an atmosphere with a non-uniform temperature. He happened to communicate this paper. After the revision, this paper was accepted, but I call that paper was the unfortunate paper. Reasons number one, in 1943, when this Obuko was just 25 years, he finished this remarkable paper. Just think about it, what we had been doing it when we were 25, and just compare that what Obuko did. He put a classical paper in the area of boundary layer, but because of World War II, lot of fund cuttings were there, probably similar to what we are presently facing due to Corona. Lot of fund cuttings. So this particular paper appeared in the limited number of journals. That time we don't have internet, so all the things were hard copy. So this journal got circulated only to the few number of people. That also it was in the Russia. So no one actually knew what is this paper about, and it became almost like in the buried way for years. We have to blame the Second World War, which took away all the funds, and this particular scientific paper went to the coal box. So that is why I call this paper was very, very unfortunate. Remember the year 1943, 1946, it got accepted. So that means you communicate a paper to a journal, you wait for 3 years to get acceptance. Can we do that? We cannot do that. Now, crux of this paper was he gave one introduction of the length scale L, which we call the Obuco length kind of things, and he eventually linked with the turbulence. That was the beauty of this particular paper. And he said the mean wind and temperature profile must be determined by some universal function of the uniquely defined dimension. Can you do that?
Bala Subrahamanyam, sorry to interrupt you.
Crux of this paper was he gave one introduction of the length scale L, which we call the Obuco length kind of things, and he eventually linked with the turbulence. That was the beauty of this particular paper. And the mean wind and temperature profile must be determined by some universal function of the uniquely defined dimension.
Bala Subrahamanyam, sorry to interrupt you.
Crux of this paper was he gave one introduction of the length scale L, which we call the Obuco length kind of things, and he eventually linked with the turbulence. That was the beauty of this particular paper. And the mean wind and temperature profile must be determined by some universal function of the uniquely defined dimension.
Sorry to interrupt you.
Crux of this paper was
can you please make your full screen mode? Go to view and make your full screen so that it will be.
Okay. The beauty of this particular paper. Can you please confirm once I am going for the full screen? Is it full screen now? Can you please confirm?
It takes some time to visualize.
Yeah. Dear audience, sorry for the interruptions. We have to cope up with this technology. Hope the full screen will be seen soon. Has it come full screen? I am waiting for the confirmation.
Bala, you have to go to view, then we have to click on full screen.
Yeah. I have shared the full screen.
Even you can click on edit, then either one. You can click on edit and full screen option will be there. Just click it.
Just let me just see.
Yeah.
Is it coming now?
Yeah. Is it coming now? Yeah.
So, okay. So I may like to continue. Is it okay?
Yeah, you can continue.
Okay. So the crux of this particular paper was one new length L was introduced by Obuco, wherein he said that this is the important things which tells that what will be the interaction levels between two particular bodies. Now, if I further go, he also introduced one term L as a function of U star, which we call the friction velocity, and that gives a complete new theory which need to be digested by that particular period people, right? So there was one new concept which was introduced in 1946, which was also dealing with how the atmospheric boundary layer in the lowest part interacts and how we can quantify this particular part. That was by Obuco. Now, this is what I am explaining the same things in the L, which people know. So, for the lack of time, I may skip this particular portion. But important point in this paper was a new definition L came into picture, which defined how the boundary layer will behave. Almost 5 to 6 years later, Obuco student Monin, he took over and he published one paper which English says that characteristics of the microstructure of the wind in the surface layer. They divide a new wire anemometer which is 19-degree angle, and they defined that this is how the theory should come out. So if someone looks into the time scale 1946 to 1951, 6 years later his student published with a theory actually proposed by Obuco. But today's date we understand that theory as the Monin-Obuco theory. Monin was student, Obuco was guide. Also, let us not forget, Obuco was the person who put forward this theory when the entire thing was against that. That means the entire world war was happening, and that is when they have to do the research. So that particular paper appeared in 1951. Now, if you look into this MO similarity theory, or I can say the Monin-Obuco similarity theory, the important points put forward by them also cited: number one, the fundamental experimental work at the Geophysical Main Observatory Leningrad, which was directed by Lachman, Butko and other people. They also cited logarithmic wind profile by Prandtl. They also talked of the zero plane displacement by Pesach in 1937 and Obuco length himself, which was defined in 1946. Those people who have submitted 1 or 2 papers in the boundary layer meteorology, they will always see, they always say that with humble respect to Obuco, don't call that Monin-Obuco length, call that as Obuco length, because length was defined by Obuco, whereas the theory was defined by Monin and Obuco. So the theory is known as the Monin-Obuco similarity theory, but the length is called the Obuco length. Now, further to that, if I go, this is the 50 years of Monin-Obuco similarity theory, which in the boundary layer meteorology in 2006 it got published. The left side is Monin, who was student, Obuco on the right hand side. Those who are interested to look for what is the MO similarity theory and how it has evolved, I would suggest them to pick up the copy which is available in the internet also. That will give you very beautiful papers, extraordinary papers, which deserves to be read and appreciated. So with this Monin-Obuco similarity theory, I will go a little bit one more year before that, that was Charnock. Charnock paper, actually it is a discussion paper, which appeared in the QJRMS, that is the Quarterly Journal of Royal Meteorological Society. Now this Royal Meteorological Society, they have their own way of working. They will always say that don't tell so much big stories. You cut short and tell the crisp. So what they say is, if you have a big paper, submit as a paper. And if you have a very, very small thing, you put it as a small discussion. So this paper actually was a paper by Charnock. He put forward as a big paper, and eventually it came to a kind of rejection. They said that whatever you are saying is not very great. What you can do is you cut short to probably 1/10 of your length, and you submit the very crisp discussion. So he has nothing to do. He just said, okay, what I will do is I will give 2 equations and I will write what the equations means and I will go ahead with it. Acceptance of paper was more important than the rest of the things. So in this paper, he said the u, which is the velocity, which you divide by the friction velocity, it is a kind of a constant, which you see the carbon constant, and another constant, that is what he wrote here, which you zoom here. That particular thing is known as the constant, and that was 1955. The length of the paper was 1.5 pages. Someone says that, what can you explain in 1.5 pages? I would recommend them, please go to this paper and read it. And you look for the citation of this paper, which may be running more than 20,000. Why do we refer this paper? Because the idea, the crisp method, and also the content which was put in this particular paper, you won't find in big papers which are writing the stories kind of things. And that was called the Charnock paper, and later we call that as Charnock constant. Point, Charnock did not say it is Charnock constant. We call it today that it was Charnock constant. Now, MO similarity theory, add with the Charnock constant and also bring the Von-Karman. This equation, sometimes it may look slightly boring to you, but the crux of the air-sea interaction parameters starts with the fundamental equation which Bussinger in 1971 put forward, subject to Monin-Obuco similarity theory, which says that velocity at any height u should be a function of friction velocity, should be function of roughness length, and should be a function of stability function. It has been years since it was put forward, and we look into the different von Karman constant, which is changing based on the field experiment, but rock robust 0.40. That has not moved too much. And a very famous Boundary Layer Meteorology, where J.R. Garrett has given, the editor himself has given the review. This particular figure, I probably appreciate the maximum in my life. For one reason is, one scientist called von Karman gave a constant in 1950s. We are not able to shake that constant even after 50 years. Look at the experiments, 0.40 what is given, and that is the value, and that is the cadre of von Karman which he gave, which we today call von Karman constant. Very detailed review is available in Boundary Layer Meteorology here. Now, further, if you go to this one, Foucan, he also happens to be one of the famous authors who has done a lot of work in the solar eclipse and also in the area of Boundary Layer Meteorology. He has further gone beyond that the stability functions, how do they vary? The important things for us to know here is, why are these all authors doing the work here? To get the sensible heat flux, latent heat flux, and momentum flux, because these three things are your budget equations. Something like somebody asked me, what is my salary? How much of amount goes to food? How much of amount goes to housing? A maximum portion goes to the boundary layer. So unless you address that particular point, you will never be able to understand the air-sea interaction. So that is how the air-sea interaction and the atmospheric boundary layer goes hand in hand, and they have been going hand in hand. So if you look into the Obuco equation and probably some of the works done by my institute from 1953, and my institute started from 1984. So 1984 onwards, if you look into that, we might have probably published more than 25 papers in the area of Monin-Obuco similarity theory. But theory is rock rigid, rock robust. The Kansas experiment, which says over the very homogeneous terrain, we are unable to shake. And the time has come to look more deeper into the oceanic part. So I always appreciate those people who go to the sea and collect some in situ data. Please remember one point from me: if any time in life, each and individual data which you are collecting is worth billions of dollars. If it is a cyclonic observation, it may be worth billions of dollars. Each observation, whether it is sea surface temperature or air temperature or humidity, you do not know what is the consequences it will be having at the later stage. So those who are collecting data, my big salute to all of them. And about the presentation, what I put forward, take home message, I will give 5 important take home messages. Number 1, Ludwig Prandtl, he gave a seminal paper on the motion of fluids with little fraction. He never used the word boundary layer, but today we know that as the boundary layer. Second paper, Obuco, he defined the turbulence in an atmosphere with non-uniform temperature against all the odds. He never said a length. He just called one length scale. Today we know to know Obuco length. Again remind, Obuco did not say it is Obuco length. Next to that, Obuco also put forward characteristics of microstructure in the wind in the surface layer in atmosphere. Subject to next was the Monin and Obuco. They never said it is Monin-Obuco similarity theory. They said it is similarity theory, and it today known as Monin-Obuco similarity theory. Last but not the least, Charnock, wind stress on a water surface, QJRMS, which was forced to change to a discussion paper. That means make it very short. And below I say first of its kind. But surprisingly, all these papers definitely were first of kinds, but nobody claimed that it was the first of its kind. Rest is history. So self-drumming is very easy, but this why people, if you take out from the history, in the area, the domain, in the World War when they did, these humble people never claimed that we did great work. Rest is history. So what work we are doing, it may be great. Years later, probably we will get to know that we have done some discovery. So the atmospheric boundary layer, which was a neglected topic for decades and years, it got eventually importance, and today's date, all the aerodynamics, all the rockets which fly from ISRO, NASA, ISRO, whether you go to the cyclone study or something, you cannot ignore this particular topic because it was not studied. We have to pay the attention, and we definitely pay the attention. So with this particular words, I would like to close my talk firstly to thanking all of you for your time, and I will like to give a philosophical message as Dr. Prasad already told. My favorite guru, he says, Radhanath Swamiji, earn with integrity, spend with compassion. What does it mean? When you are earning some money, when you are earning some assets, please don't go to the corruption. Earn with integrity. Don't spoil your integrity. When you are collecting the data, earn it with integrity. Don't worry about the results kind of things. And once it comes to the spending part, don't be greedy. Spend with compassion. Compassion is something which will drive you to the larger heights. If someone quotes Ratan Tata, he has done so much for country, not because he is a millionaire. He has a compassion for the country. So with these remarks, I thanks all of you for attending my seminar. Here is my email ID, and now I will stop the sharing presentation and probably questions which I would like to address. So I will hand over to Dr. Prasad now. Dr. Prasad, I am sharing. I am stopping my sharing now. We can have question answers sums. Thank you. Have I lost the link? Am I audible?
Okay, Dr. Bala, I think Prasad is not, I think he is logged out.
Okay, okay.
It was really very interesting, and the journey of boundary layer has come out very nicely.
Okay, fine.
Importance. I think he has come back now. Prasad, you can take over.
Prasad.
Yeah, so there are actually, thank you, Dr. Subramanyam. It's a very energetic and.
Okay, Dr. Bala, I think Prasad is not, I think he is logged out.
Yeah.
It was really very interesting, and the journey of boundary layer has come out very nicely. Importance. I think he has come back now.
Yeah.
Prasad, you can take over.
Yeah. So actually, so there are actually, thank you, Dr. Subramanyam. It's a very energetic and.
Okay, Dr. Bala, I think Prasad is not, I think he is logged out.
Yeah.
It was really very interesting, and the journey of boundary layer has come out very nicely. I think he has come back now.
Yeah.
Prasad, you can take over.
Yeah. So actually, so there are actually, thank you, Dr. Subramanyam. It's a very energetic and.
Okay, Dr. Bala, I think Prasad is not, I think he is logged out.
Yeah.
It was really very interesting, and the journey of boundary layer has come out very nicely. I think he has come back now.
Yeah.
Prasad, you can take over.
There are very few.
So actually, so there are actually,
thank you, Dr. Subramanyam. It's a very energetic and.
I think he is logged out. Really very interesting, and the journey of boundary layer has come out very nicely. I think he has come back now.
Yeah.
Prasad, you can take over.
There are very few.
Actually, so there are actually, thank you, Dr.
Okay, I think there are few questions. First question is, observations in the ocean boundary layer is very less. How can we address this issue? Maybe we can measure with drone from ship or boat.
Prasad, can you? Prasad, am I audible?
Yes, yes.
Yeah.
So the question is, observations in the ocean boundary layer is very less. How can we address this issue? Maybe we can measure with drones from the ship or boat or in the island.
Yes, Prasad, that's a relevant question by Dr. Ravichandra. I think we go with the satellite-based observations, and we have to go to the more inverse algorithms, because whether it is the drone or probably the in situ measurements, we always are having the kind of opportunity. And if we want to deal with the cyclone kind of cases, we should have some real-time measurements. So I believe in the future generation, probably 10 years from now, this gap will be filled by the satellites, and we are not too far.
Okay. Okay, good. So, yeah, there is one more remark actually which is given. It's a good introduction to the topic. It has been followed by the next talk on what has been done in BobMex, Armex, Montplex by the same speaker.
My pleasure.
You can share your experiences on that now. Yeah.
Definitely, it will be my pleasure. We can have it in probably next session. It will be different because like Armex and to the best. I have appeared.
Okay. I think these are the two questions actually which I see in the chat box.
Yeah. Actually, no, Armex and Montplex, that was in the very good experiment, and till today we refer to like or the Prabhu's paper or Rotam Narasimha. That was a very crisp experiments from Indian side. We can take it up in the next OSI talk sometimes, I think.
Okay, okay, fine. Very good, very good. So, yeah, there are actually good points in the chat box. Like, thanks a lot for the history, and we wish to hear more on its interaction and current developments.
Definitely, definitely.
Yeah. So I think these are the questions that we find in the today, and
yes.
Then yeah. So I think Dr. Ravi actually can just now maybe propose the vote of thanks. Yeah. Dr. Ravi.
vote of thanks.
Okay, good morning.
Yes, sir.
Good morning. First, Dr. Prasad, you can use either your WebEx or YouTube. You are using both. That's why these echoes are coming. Or you can mute one of the things. Okay. Thank you, Dr. Bala, for providing insight into the boundary layer. And first, Dr. Prasad.
Yeah.
So I sincerely thank on behalf of Ocean Society of India for you to giving this lecture and come forward. And it is really entirely different things, how the boundary layers journey has come and where we are now. And I think this is a very good initiative. And I think you have made a lot of effort to make this history. And we sincerely thank you. And I hope all the members as well as others enjoyed your presentation. And on behalf of OSI, once again, I thank you all. Thank you for especially Dr. Bala Subrahamanyam and Dr. Bhaskar for arranging this talk, and hope to meet in some other web forum soon. Thank you very much. Thank you.
Thank you. Thank you.
We can close now.
Yeah.
Shami, you can stop recording now. Thank you. Thank you.